All of the calculations we've done so far are using standard reduction potentials or thinking about standard solutions, 1 molar solution. But it's very common that we could make a higher or lower solution just based upon what we have or what we need in order for this reaction to occur. And we also need to remember that as reactions occur, the molarity of those things change. We produce more of one ion and consume the other ion. So we need to be able, to understand as the concentrations are changing, what's happening to my voltage or my cell potential. So as a general equation here, we know that our anion or anode is oxidized into a cation, and the cation that's in the cathode turns into the metal. There's lots of exceptions to this, but we're going to focus on galvanic cells, so negative delta Gs, and we're going to focus on simple reactions. So this could be similar to that zinc and copper reaction, where we would have one thing dissolving away and another forming our solid. For example, our zinc ion would dissolve into ions while our copper ion solidifies into solid copper, increasing the mass on our cathode. If it's 1 molar solutions all across the board, then we would know our cell potential just from our standard reduction potentials. Our molarities of both ions would be 1 molar. Q, remember, is the K expression not at equilibrium. So that would be 1/1. The metals are not going to be involved in it. So it's just 1 molar over 1 molar. And then the reaction keeps going. We would have a positive cell. We would have this. And know that our K is greater than 1. So the reaction just keeps going until the battery runs out, or really until we get into equilibrium. We get into equilibrium when this gets low enough and this gets large enough. That would be making our K bigger. When this is bigger, a product is bigger, and this is smaller, that the reaction is no longer favorable in that direction. So when we make changes, we are either adding or removing some of our cation, we are adding or removing some of our anion, and that would make the reaction either more or less favorable. In some ways, it's really tempting to use a Le Chatelier's principle argument. We need to remember that we're talking about a reaction that's much more favorable in one direction than the other. We're not talking about the equilibrium that we reach once the battery runs out. So we're not able to use that. We're talking about things like driving forces, and we're thinking about how we're changing our Q compared to how we're changing our K. If we want our reaction to go more forward, or if we want our reaction to become more favorable, we need to take our Q farther away from our K. Well, since K is a big number, we need to accomplish that by making it a smaller number. We can do that by lowering our starting concentration of the anion solution or the anode solution, or by increasing our cation. And this is where I say it has a similar feel to Le Chatelier's principle, but we wouldn't use that same word. If I put in more reactant, it drives the reaction more forward. We wouldn't say shifts forward because we're not at equilibrium, but more cation concentration is going to drive it more forward. A lower anode cation concentration is also going to drive it forward. This wants to be increased until it gets to, until it continues to react. So either of those, putting more of this in, throws this off or throws that off. Both of those lower our K value, our Q value. It takes it farther away from K, so it drives it even more in that way. But if I put more of this, more product in, it would slow down or make that forward reaction less favorable. If I take away a reactant, it can't react as much. Both of those increase my Q value. It makes my Q even closer to my K, and therefore it would make the reaction less favorable. More favorable reactions make a bigger value for voltage, less favorable make it smaller. So we're kind of thinking of shifting, but not using that word. We're saying it drives it forward. More reactant drives the reaction forward. Putting in more product decreases the forward drive and lowers the voltage. So this is something that really takes a little bit of practice to get the wording right, but we can also think about it mathematically. This equation is called the Nernst equation. It's given, and you can use it, but you won't have to do exact calculations, which is really nice. This is our standard cell potential, E naught cell. So that's our standard cell potential. R, T, N, and F would be constant for whatever cell that we are in. R is a given. We would be at some temperature. We would know how many electrons, and Faraday's constant's also a given. So we're really focusing on the Q. Did we increase or decrease our concentration of reactants or products? And that's why I had this column right here. But if we're really just thinking about it as products over reactants, we can do the math on this. The natural log of a number that I'm making even bigger makes a positive number. So that means I take my cell potential and I subtract some away. It lowers my voltage. So if I put in less reactant, or if I add in more product, if I put in more of this or I lower this, the reaction can't go as fast or as favorably. But if I put in more reactant or take away some product, then I make a Q that's less than 1. The natural log of a decimal is a negative number. So a number minus a negative number becomes even more positive. So we can think about that. We can do those calculations. We can do those estimations. But when we're talking about this, we're really talking about, am I changing this or this? And is it driving it more forward or not? Some examples right here in a non-standard cell, I could see I've got a certain voltage, but as this goes on and goes on and goes on, my voltage is actually dropping. I have more stuff here, so my concentration of my cation has decreased. I've got, or my colors are changing. Sorry, I'm running out of this, so I have more of that. This is going to be driven less and less and less forward because I am running out of my reactant. I am making too much of my product, and the cell starts to die. So it says right here, we can change the molarity ourselves, putting in different solutions, but standard cells, if I've got my 1 molars, eventually die over time. And that's important to note as well. We run out of cathode, cation. We make too much of this. This concentration is getting too high. This is getting too low, so it can't run as favorably. It's also possible to play with certain cells where we're looking at different concentrations. So this would be a concentration cell. It can be used in plating a lot, meaning if we're trying to get a certain concentrate, or we're trying to get a metal to cling to or form a solid in a certain place. The idea is similar, that we have a Q that isn't equal to, or that is further from our value of K that drives it even more. Or right here, I have too much nickel and not enough nickel. This one needs to dissolve away. This one needs to solidify until we have the same voltage in each. Concentration cells are not very common here in AP Chem, but just wanted to introduce that it's another application that is important. And it's the same idea as we still reduce at the cathode, oxidize at the anode, electrons flow from the anode to the cathode, and they continue to flow until the cell is no longer favorable. So we're not going to think about exact voltage, but we could recognize why something may be driven by thinking about qualitatively the Nernst equation or how to apply those concepts.